Hello everybody, today we're starting off the Economics 201/205 Macroeconomics lectures. Because of the unrest, I decided to do a couple of introductory videos so that you have access to them and perhaps so that you can view these prior to the start of lectures. The course starts with a discussion of growth and accumulation, and specifically economic growth is a really important macroeconomic objective. Economic growth in quantitative terms would refer to increases, specifically percentage increases, in gross domestic product over time, and in particular real gross domestic product over time. So we measure economic growth as the percentage change in real GDP over time. And economic growth is really essential for countries to do and perform well, because without economic growth, it is not possible to improve the living standards of a country's citizens. So that's why we are very concerned as macroeconomists about the amount of economic growth, and why there have been numerous theories that we then try and use to understand not only how economic growth occurs, but how countries can go about improving their levels of economic growth. So I'm going to do two different videos for this session. It's a combined session, session 1 and 2, so I'm going to split the videos up. The readings for both of the sessions come from your textbook, Dornbusch, Fisher and Starts. You can use the 13th, the 12th edition, or the 11th edition. The 11th edition readings are provided in the Macro 1 outline, which is on Moodle. The point really of these two lectures is to explain economic growth imperatives, in other words, what's essential for economic growth, to introduce the production function as a way of analyzing economic growth, and to show how factors of production contribute to the expansion of output. In other words, how the role of inputs is very, very important in trying to understand how an economy grows. All right, so let's get started. As macroeconomists, there's probably two important questions that we would want to ask ourselves. The first is that when we think about economic growth and we start comparing economic growth rates across different countries, we would want to probably start wondering, well, why is it that some countries grow really fast and other countries don't appear to grow very fast at all? So why are there such big differences in economic growth rates between countries? What's going on? What can explain the difference in economic growth rates between countries? And the second thing that we would probably start to wonder is, well, how come, and this would happen if we start looking at how economic growth in particular countries has changed over time, we would start to wonder, well, why have countries which started out with really low economic growth rates, why have some of them been able to catch up to the economic growth rates of the more developed countries? And then, similarly, why have other developing countries not been able to catch up to the growth rates achieved by the more developed countries? So why do some of these countries, why are there still differences which persist? And the questions that we've just posed above can be answered by both growth theory and growth accounting theory, and we're going to be discussing aspects of both of these in the course. Before we get though to those growth theories and to try and understand those differences that exist between the two different types of theories, have a look at the figure on the right hand side of the screen. And what this is showing is changes, well, it's not showing changes, but it's showing levels of GDP per capita for 4 countries over time, specifically the US, Japan, Norway, and Ghana. And what we can see is on the horizontal axis, we have our timeline. This graph starts off in the 1820s and continues with information up until the 2000s. On the vertical axis, we're measuring GDP per capita in 1990 dollars. So just to remind ourselves, GDP is gross domestic product. Per capita means that we're talking about gross domestic product per person. So for the countries which are being shown here, what's being plotted is a living standards measure in each year. Also note that these are real values. They are $1990, okay? the values have been expressed in terms of $1990. And if you recall, because of the effects of inflation, it's important when we look at GDP or GDP per capita over time to always use real values. Otherwise, our figures could be overstated by the effects of inflation. And then the final thing to just note is that because these countries all would have different currencies, a similar currency is now being used for the comparison. And so all of the countries' GDP per capita values have been converted into dollars. What we can see is that all the countries shown start off at approximately the same point. So the US and Norway, which is shown in light blue, and Japan in grey, and Ghana in black, although Ghana does lie a little bit below these others initially. But they all start off in the 1820s with very low levels of GDP per capita. And time moves along, and what we can see is that some countries, specifically the US most predominantly, but also Norway and then Japan, they start to increase their levels of GDP per capita. And if you take the US, for example, this increase really starts to take off into the 1900s. It tapers off a little bit during the war in the 1930s and in the 1940s, and then it continues to increase relatively rapidly into the 2000s. Okay, so GDP per capita levels started off really low for the US, but then there was quite a big escalation in GDP per capita and living standards rose relatively rapidly. A similar finding can be seen for Norway, although overall their levels of GDP per capita are lower than those for the US. A similar trajectory is shown. For Japan, their levels of GDP per capita are also lower than for the US, but note how particularly in the 1970s and into the late 1980s, you can see points where the Japanese line starts to touch the Norway line. And that would suggest that there has been points where Japan and Norway would have converged or had the same levels of GDP per capita, despite in some cases having quite big differences in GDP per capita. And then we have Ghana at the bottom, which really, if you think about a heart rate monitor, just seems to have flatlined. Okay? Ghana had really, really low levels of GDP per capita in the 1820s, and over time, all the way into the 1950s, it really hadn't changed very much at all. There was a bit of an increase in the 1950s, but if you continue to look at the levels of GDP per capita in Ghana, they really haven't increased by much at all, and there certainly has been no evidence that levels of GDP per capita would come anywhere close to those of the more developed countries like Norway or Japan or the United States. So this then begs the question, well, first of all, what did countries like the US and Japan and Norway do that enabled them to get economic growth increasing to such an extent that their GDP per capita was then also able to increase really rapidly? And then the other question is, well, what's Ghana doing wrong? Why haven't they been able to increase their levels of GDP per capita so rapidly? So why does there continue to be such a gap between countries like Ghana, and we could throw, Bangladesh, for example, into that kind of situation of countries as well, with really low levels of GDP per capita that haven't been improving much over time. So why are there countries that have that situation versus countries that are able to achieve increasing living standards, and in addition, countries that have been able to catch up to other countries? So we're going to look at two different types of theories that allow us to consider these. The first theory that we're going to be looking at is called growth accounting theory, and the second refers to a series of theories, and those would be called growth theories. So with growth accounting theory, what we're really interested in is understanding how inputs lead to outputs, and in particular what the contribution is of different sorts of inputs into the output that gets produced. So growth accounting theory, a definition of it would be that growth accounting theory tries to explain what part of growth in total output is due to growth in different factors of production. You'll recall from last year that factors of production are the inputs the items, the land, the labor, the capital, the entrepreneurship, and the technology, for instance, which are used to produce the goods and services that a country then uses or sells to other countries. And it's those goods and services which then form our gross domestic product. So growth accounting theory is really about trying to understand how these different factors of production contribute to economic growth. Growth theory, on the other hand, says to us, we say to ourselves, well, okay, we know that we need inputs in order to produce more outputs, and growth accounting theory is kind of dealing with that. Growth theory takes it one step further, and it says, well, how can we go about obtaining more inputs in order to get more outputs? So the theories are complementary, but they're also slightly different. Growth accounting theory says we need more inputs in order to produce more outputs. Growth theory, on the other hand, says yes, we need more inputs in order to produce more outputs, but how do we get more inputs to produce more outputs? So one way of thinking about the difference between the theories is that with growth theory, you're going one step further. You're asking yourself, how can a country achieve more inputs in order to achieve higher growth rates? Whereas with growth accounting theory, the how doesn't really fall into the picture. It's merely trying to understand what the contribution is of different inputs to the output which gets generated. Alright, we're going to look at both of these different theories, but we're going to start off by looking at growth accounting theory. Growth accounting theory conceptually is very simple. It essentially says that output will increase if you have more inputs. Now, this makes more sense. That makes a lot of sense. If you increase what you put into production processes, you would hopefully expect that you should be able to get more out. So increasing our inputs will increase output. Inputs could be things like capital, here denoted by an uppercase K, or labor, here denoted by an uppercase L, although you'll see later on that we actually switch and use N to denote labor. Okay? Increase your inputs, you will get more outputs. In addition, even if you don't have more inputs, it's possible to increase the amount of outputs by improving technology. So increases in productivity will be able to ensure that countries can use their existing factors of production, their existing resources, more efficiently to produce more. So we also do kind of recognize that yes, well, you need more going in to get more out, but also if you don't have more going in, if you are able to use what you have better through technological improvements, then you may also be able to get more out, more outputs. The other thing which can influence the amount of output being produced is the quality of the workforce or the quality of the labor. So things like educational improvements over time and improvements or increases in health standards, those would also be able to assist in achieving more output over time. In order to understand the link then between inputs and outputs, we use something which is called a production function. And the production function is a way of establishing a quantifiable or measurable link between inputs and outputs. A production function enables us to understand how increases in capital stock, the labor force, and technology, for example, will affect the amount of output being produced. We're going to consider a really simple production function where we only are dealing with capital stock, labor, and technology. Of course, you could include other inputs in there, but for now, we just want to keep it simple. So our production function in mathematical notation is capital Y is a function of A, okay, which is technology, as well as K, which is capital stock, and N, which is the population size or labor. Note that these are all uppercase letters, and that's because these are all referring to aggregate or total levels of output or total levels of capital or total levels of population sizes or total amounts of technology. What they're not yet referring to, and we will have to transform that production function into growth rates in order to be able to do this, but for now, that production function is all in levels. It refers to aggregate output being determined by the total amount of technology and the total amount of capital and the total amount of labor. What you should notice is that if you were to increase what's on the right-hand side, if the values of capital or labor were to increase, output would increase. In addition, even if capital and labor don't increase, increasing technology would be able to increase output. And this is because technology augments the amounts of capital and labor being used in the production process. All right. To continue our discussion, we need to understand how it is that changing the amount of inputs goes about and then causes an increase in the amount of output. And to do this, we have to revert back to our Economics 101, where you would have learned about things called marginal products. And in particular, we're interested in two different types of marginal products. We're interested in the marginal product of capital, and we're also interested in the marginal product of labor. Now, the marginal product of capital tells us if we increase the amount of capital stock by 1 unit, how much will output increase by? So the marginal product of capital is measuring the amount by which output increases when capital stock increases by 1 unit. Similarly, the marginal product of labor is measuring by how much output increases when the amount of labor is increased by 1 unit. So essentially, the marginal product values are telling us how much we get out for each additional unit of the inputs that we put in. Alright, with that in mind, we are now going to move to a specific example of a production function, and the production function that we're going to be working with is called the Cobb-Douglas production function. A general production function would have been this one here. It's a general form of a production function, the one which we used to explain initially. But in economics, we often use this production function called the Cobb-Douglas production function, and I'll explain a little bit more just now what the values of theta and 1 minus theta are for. But essentially what it's important to know is that the Cobb-Douglas function takes on a form which looks like this or similar to this, and that the exponents on the capital and the exponents on the population size, theta and 1 minus theta respectively, will sum to 1. And that's a really useful property for the production function to have in economics, because it means then that there are constant returns to scale. And that's why we then use the Cobb-Douglas production quite a lot in the work that we do. Alright, what we want to do then is try and use this Cobb-Douglas production function to work out what the marginal products of labor and the marginal products of capital are. What we are going to assume is that the marginal product of capital and the marginal product of labor are both positive. Now this intuitively is a very important thing to have, because what it's suggesting is that there is this positive relationship between the amount of capital put in and the amount of labor put in, and then the amount of output which is being generated. We are essentially saying that there's a positive relationship between the amount of capital stock and output, as well as the amount of labor and output. So increasing capital stock and increasing labor will increase output. Alright, the marginal product of capital is given as follows. The marginal product of capital is the change in total output divided by the change in capital stock. So when we change our capital stock by 1 unit, by how much will output increase by? I'm going to show you how we get to this value, but for now it is theta y over k. That will give you your marginal product of capital. The marginal product of labor is then the amount by which output increases when the labor or population size changes. So just note the small mistake here. This should be change in n in the denominator. So what the marginal product of labor is telling us is when we change labor by 1 unit, by how much will output change? And the marginal product of labor is then given by 1 minus theta y divided by n. Alright, what I want to do is just switch the screen so that I can show you how we will go about getting those two different marginal products. Okay, so we're going to use, if we had our, to make sure that you can see here, our general form production function, AFKN, okay, and we're going to use specifically the Cobb-Douglas version of that production function, 1 minus theta. Okay, so that's our general form production function. On the right-hand side, you have the Cobb-Douglas production function. The marginal product of capital is then going to be equal to the partial derivative of the Cobb-Douglas function with respect to capital stock. Because what we're interested in is the amount by which a change in capital stock will change outputs. So if you recall back to your calculus that you would have done perhaps in first year, that will, taking partial derivatives is what allows you to work out these partial changes. So the marginal product of capital would be equal to dy over dk, which is then equal to theta a k theta minus 1 and n 1 minus theta. Okay, so remember when you take the partial differential, or partial derivative, the exponent comes to the front and then you minus 1 from the value that you are dealing with. Okay, so we then continue through and we have k theta, k to the minus 1, L 1 minus theta, and that is equal to theta a k theta L, this should be n 1 minus theta. And what you should then notice is that this part here is simply the Cobb-Douglas production function. Okay, and this should all be over. Okay, and then what we therefore have is theta y over k, and that is our marginal product of capital, which you would have seen in the previous slide. Okay, similarly, let's move this across. If we wanted to do the same thing for labor and work out the marginal product of labor, it would be dy over dn. Okay, and that would be 1 minus theta ak theta n 1 minus theta n minus 1. And that is equal to 1 minus theta a k to the theta n 1 minus theta all over n, which is equal to, again, note what happens here. This is the Cobb-Douglas production function. So 1 minus theta y over n is our marginal product of labor. Okay, so what I've just shown you is how you take the partial differentials of the Cobb-Douglas function in order to work out the marginal product of capital and the marginal product of labor. And what we're going to then do is switch back to the slides. Okay. Alright, what we now want to do is translate the production function into growth rates. Now there is extensive maths which one needs to go through to do this, but there are already a worked set of examples for this at the end of these slides. And to be frank, it's quite frustrating to talk through the different lines of maths. So it's done line by line at the end of the slides, and I suggest that you go through those. Suffice to say that when we translate the Cobb-Douglas production function into growth rates, we end up with something called the growth accounting equation, which is this equation here. And what is it suggesting to us? Well, it's suggesting that the growth rate in output depends on the growth rate of capital stock as well as the growth rate of the population, as well as the growth rate in technological progress. In addition, it depends on theta and 1 minus theta. Now, I haven't really spoken about those, so what are they? Theta refers to the share of capital in total output growth, and 1 minus theta refers to the share of labor in total output growth. So, in other words, what we are saying is that the contribution of labor and capital stock to total output growth may not be equal. It's possible that capital contributes more to total output growth than what labor does, or vice versa. In fact, it's actually the case that capital stock contributes less. The share of capital stock in total output growth is usually less than the share of labor in total output growth. But think about it this way. Imagine that one is producing a pie, and there is labor and capital which goes into the production of that pie. Essentially what we're asking ourselves, well, how much of the pie was produced by the labor, the cooks, and how much of the pie was produced by the oven that baked it? So we're kind of working out the contributions of the labor and the capital stock to the total output. Okay? Also note that this is quite different from the Cobb-Douglas production function, because the Cobb-Douglas production function, shown here, is in levels. It's aggregate output and total technology, total capital stock, and total population size. Whereas here, this is then a growth accounting equation, because we're no longer dealing with levels or totals, we're dealing with growth rates. Change in Y over Y is the output growth rate. It's measuring how much output changes from one period to the next. Here, change in K over K is measuring capital stock growth, and change in N over N is measuring the population size growth. Change in A over A is measuring technology growth. Okay, so this is essentially our growth accounting equation. And we are able to then use this to understand a little bit more about how the different components, capital stock, labor, and technology, contribute to output growth. An important thing to note is that technological progress, also sometimes known as total factor productivity, can also be gauged from this equation, specifically if you make the technological change or total factor productivity component the subject of the equation. So that's what's being done here. In this line, we have the technological progress, which is then made the subject of the equation. And what it's suggesting is that technological progress, the measure of total factor productivity, can be obtained if you know what the economic growth rate is, and if from that you subtract the contribution to total output growth made by capital stock overall, and the contribution to output growth made by changes in the labor stock and the population size. Okay, so essentially, total factor productivity or technological progress is the change in production which takes place, which is not due to changes in factor input quantities. All right, so to try and understand a little bit better how this works, we are going to go through a worked example. So I'm just going to copy these down on my page. You can start looking at them there. We've got theta is equal to 0.3. Labor force growth, which is change in N over N, is equal to 2. Growth in capital stock, change in K over K, is equal to 3. And total factor productivity, change in A over A, is equal to 1.5. All right, let me switch the view back to the paper view. Okay. All right, so these values here are the values which I obtained from the question which is in your slide. And we now need to use the growth accounting equation in order to try and find out what total output growth is given these values. So the growth accounting equation says that economic growth or total output growth depends on theta multiplied by capital stock growth plus 1 minus theta multiplied by the population size changings, or the population growth, as well as the amount by which technology changed. Okay, so now we simply substitute the values in. Theta here is 0.3. So that's suggesting that the share of capital stock in total output growth is 30%. Okay? And the growth rate in capital stock was 3%. So we can put 3 in there. Note that you don't have to convert these into 0.3 for percentages. So here, 0.3 is the share of capital stock in total output growth, but we were told that the capital growth rate was 3%. So I don't now go 3 divided by 100 to get 0.03 and put that in here. I can just use the whole number, which is 3. Okay. 1 minus theta would be 0.7. So that's suggesting that the population size's contribution to total output growth is 70%. The growth rate in the population was 2%, so we can put 2 in there. And technological change was 1.5. Okay. And we're going to keep these separate, plus 1.4 plus 1.5. And when we add those up, it's equal to 3.8%. Okay. Now, what you should notice is that we can see quite clearly what the different components were contributing to total output growth. Capital contributed 0.9 of this 3.8%. So 0.9% of the 3.8% growth in total output was contributed by the growth in capital stock. Over here, 1.4% of the 3.8% increase in total output was contributed by the growth in the population size. And the remainder of 1.5% was contributed by technological change. So these three things together contributed to total output growth. So what our growth accounting equation is able to do is tell us which of the different inputs were contributing the most to total output growth. And given the figures in this example, technological change was contributing the most to output growth. The other thing to note, though, is that the growth in the capital stock was actually the highest. Okay, the capital stock growth rate was 3%. But because the share of capital stock in total output growth is only 0.3, in other words, because the share of capital stock in output growth is lower than the share of the population in total output growth, overall, the contribution of capital stock to output growth is lower than the contribution of labor to output growth. Okay? So when the factor has a low share in the production process, even if its growth rate is high, it may not contribute a lot to total output growth. Whereas something which has a larger share in the output growth process, even if its growth rate is low, it might end up contributing quite a lot to total output growth because its share in the production process is quite high. Alright, there's another example to go through, so let's just go back here so that we can see what it is. There we go, slideshow. Okay. So the second example that we're going to go through says if we assume a Cobb-Douglas production function where the share of capital is 0.2 and the share of labor is 0.8, then the marginal product of labor is equal to, okay, so we need to work out what the marginal product of labor is equal to. So I'm just going to write those things down. The share of capital is 0.2, the share of labor is then 0.8, and you are asked what is the marginal product of labor. Okay. So let's switch back to here. Okay. Alright, so what is our formula for the marginal product of labor? Well, the marginal product of labor, if you recall, and this is where we went through the mathematical notation in order to try and work out the marginal product of labor. The marginal product of labor is the change in output that takes place when the labor force changes, or when the population size changes. And that's equal to 1 minus theta y over n. So this one's really quite easy, okay, because 1 minus theta is 0.8 y over n, which is equal to 4 over 5 y over n. Okay? And if we go back to the slide, you will see that that is exactly what we have worked out. Oh dear. And in particular, let's just go through here, and in particular that the answer is A. Okay. Alright, at that point I think I am going to stop, and we will continue this in the next video. Just so that you know where we are going with this, up until now we have looked at the growth accounting equation specifically, and that has enabled us to understand how different inputs can contribute to total output growth. We've learned that the share of the different inputs in the production process is very important, and in particular that where inputs have a low share, even if they grow quite fast, overall they might not contribute a lot to total output growth. And sometimes, if there are inputs, often labor, where their share in the production process is quite high, they might end up contributing quite a lot to total output growth, even if they themselves are not growing at a very rapid rate. We also learned that it was important to recognize the role that technology plays. Because technology can augment capital stock and labor, the effect of technology on total output growth is additive. It doesn't have a share. And so if technological progress is happening at a rate of 10%, well then your output growth should be increasing by at least 10%, and then increasing even more depending on how much capital stock and labor stock are increasing by. The next thing that we're going to do in the next video is translate all of this into growth rates in per capita output, because that's the way that we then can understand how living standards are improved. Up until now, we've been dealing with growth rates in economic growth rates, which is your percentage change in GDP. What we want to move to is to try and understand the percentage change in GDP per capita and what determines that. Because if we understand how living standards are improved over time, then again we are able to understand what the different inputs are and how they can be used to try and improve living standards over time.